Hi, my name is Koskiewicz, and this is my physics extra credit problem. First, I determined the speed of the jumper at the bottom of his swing, and I did that by calculating delta U equal to delta K, and I just used the mg delta Y equal to 1/2 mv squared. So then we're going to get the m's to cancel, and we're going to have 9.8 times my delta Y, which we estimated to be about 150 feet. That's about how long the rope was, which is about 45.72 meters. So multiplied by 45.72, because that is a change from the top of his swing until he's at the bottom. That's the total difference in displacement. And then we're going to have this equal to v, and the 1/2s move over, and we have the square root of this. So this whole equation is my velocity at the bottom of the swing. And we figured that out to be 29.94 meters per second. Okay, so for the next part, we had to figure out the tension at the bottom of the rope. And this is a little bit more complex process. Normally, if the rope was just hanging there, you would just figure out the mg, the opposite would be the force of the tension. But since he's moving in a circle, we have to figure out the centripetal force, which you figure out by doing mv squared over the displacement again. And you end up getting 2,352.5 newtons for the tension force, which is about 3 times the force of gravity. Then we also had to calculate the speed and tension when it's 30 degrees. So what I did was just use the cosine of the angle and figured out a new displacement, and the numbers for that were similar. It was 2,263.4 newtons, which is like 2.89 Gs, and then the speed was 27.86 meters per second at that point. The next part, we had to figure out the stretch at the bottom of the swing. In order to do that, you need the Ks, which we found online to be, for like Kern Mansell rope, to be about 176,000 newtons per meter. And since the rope is 45.72 meters, then you have to put that newton per meter over the number of meters to get your actual Ks effective. And you set that equal to tension force, because the spring force and the tension force are equal. So tension equals KSS. And you solve for S, and you get S to be at the bottom, 0.61, and at 30 degrees you get it to be about 0.588 meters. I have the F net, and also I have the momentum vectors displayed on there. We had to do all our calculations again with the code, and all my calculations were pretty similar. Okay, so right about there. So we go into the shell, and we can see that the new final position is negative 46.3, and the length of the rope originally, the L knot, is negative 45.72. So that's about 0.61, which is exactly what I predicted. And the velocity is also very close. I had 29.94. This says 29.83. This is probably just because this is not exactly the middle of or the complete bottom, but otherwise it seems pretty accurate. About 30 degrees. And all my calculations are about correct again. So it's relatively accurate. And the final part of this is to talk about the computational model with the rope having like very little stretch, and this has very little stretch already because the Ks is so high. I found the Ks by looking at Kern Mansell rope, like I said before, and it's 176,000 divided by the 45.72, and I placed that in my code right up here. And I guess that's it.